Hello, this breakout session is about FPGA timing constraints and timing closure deep dive. My name is Weng Yu, and I am an application engineer in Lattice Semiconductor with close to 12 years of working experience in the FPGA industry. My areas include timing closure and design optimization. I also perform competitive analysis using major FPGA software tools. Before joining Lattice, I worked in Altera, and I have a master's degree in electronic engineering from the National University of Malaysia. There are 5 sections in this training as shown here. We will start off with the concept of static timing analysis and why it is important in the design cycle of FPGA. Then, we will move to the basic of timing constraints, which are needed to fully constrain a FPGA design. We will also touch on the priority or precedence of timing constraints. Then, with the knowledge of static timing analysis and timing constraints, we will look at how Lattice Radiant software accepts and treats these timing constraints in its process flow. After that, I will guide you on how to interpret the timing reports produced by Radiant. And finally, we will move to the topic of timing closure with Radiant, followed by some frequently asked questions. So let's begin. The first topic for today is static timing analysis in FPGAs. So what exactly is static timing analysis or STA? Well, STA is a method used in digital circuit design to verify the timing performance of a circuit without requiring simulation of its functionality. It assesses whether a design meets its timing constraints and operates correctly at the intended speed. There is another type of timing analysis, which is called dynamic timing analysis, which aims to do the same thing, but is simulation based. The table below shows the key difference between the two. The most obvious difference between the two is that unlike dynamic timing analysis, static timing analysis does not require any stimulus vectors. Well, this is important because in large and complex designs, having a large amount of stimulus vectors will make the runtime very long and hence not very practical in these large and complex designs. However, do note that static timing analysis only checks for timing, while dynamic timing analysis checks for both timing and functionality. Now that we know what STA does on a high level, the next question is how does it do that? Well, STA primarily checks on two things, which are setup time and hold time. Setup time is the minimum amount of time that the data input must remain stable before the capture clock edge. Hold time, on the other hand, is the reverse, which means it is the minimum amount of time that the data must remain stable before the capture clock edge. Simply put, the data must remain stable long enough around the active clock edge in order to be captured correctly. Failing either setup or hold time requirement will result in a condition called metastability, where the output of the logic element is uncertain and could lead to functional failure. In this timing diagram, data A should be stable before the indicator setup time, also known as TSU, highlighted in yellow. Now, because the transition happens after that, this fails the setup time requirement and might result in metastability issue. Just like what we discussed earlier, static timing analysis in FPGA checks for both setup and hold time requirements in all constraint paths in the design to verify if there are any possible timing violations. This is made possible by the usage of timing model in the target FPGA devices, which contains all the cell and interconnect delays. Now, these delays are then used to compare with the user-provided timing constraints. Any timing violations will be flagged and reported by the tool in the timing report. Considering the constraints are done sufficiently and correctly, users will need to fix these timing violations to ensure that their circuits are behaving expectedly. To go a bit deeper, there are a few parameters that would affect these delays in our devices, which are process, voltage, and temperature, otherwise known as PVT. Process accounts for the variation in different devices coming out from the fabrication process. They are all tested and bin into different speed grades, but will still have variation over that process. Voltage covers the fact that the voltage will vary over time, which would influence the device to run either faster or slower. A higher voltage generally makes it run faster. Finally, there is temperature, where a temperature which is lower generally means devices run faster. The timing model in Radian includes multi-corner timing analysis to ensure that the design functions across all worst-case scenarios. Now that we have talked about the importance of static timing analysis, let's move on to the basics of timing constraints. At its simplest form, there are three main types of timing constraints. The first and most important one is clock definitions. The constraint create clock is used to create base clocks, which has two major purposes. The first one being to define a clock coming to the FPGA, while the second usage is when the constraint does not have a target, which means that this is a virtual clock, which is typically used for input-output or I/O analysis. We also have the constraint create generator clock, which is used to create clocks derived from a primary clock source. Well, some common use cases are the output of clock dividers, clock multiplexers, source synchronous outputs, and even ripple clocks. Once we have defined all the clocks in the FPGA, we will also need to describe what is happening outside of the FPGA. This is done through the constraint set input delay and set output delay respectively. Both constraints will have a dash max and dash min arguments which dictate the delays happening outside of the FPGA, which include baud delay and intrinsic delay of the external devices. The last constraint type is known as timing exceptions. They are known as timing exceptions because they change the default timing analysis requirement. Since static timing analysis analyzes all paths in the design, there could be scenarios where certain paths do not need to be analyzed. In this case, set pause path could be used to exclude them from being timing analyzed. This is generally used as a synchronous transfer path where timing does not really matter. Another timing exception constraint, set multi-cycle path, is used to modify the default setup and hold relationship between the source and destination clocks. This is often used to relax timing requirements in cases where data can be captured over multiple clock cycles. Last but not least, the constraints set max delay and set min delay are used to define an arbitrary setup and hold requirement, respectively. Unlike multi-cycles which are based on clock edges, users can define any value they desire using these constraints. Timing constraints will need to be applied correctly to the correct design objects to be effective. Shown here is the list of different design objects, depending on where you want to apply the constraints to. We will begin with cell, which could be an instance of a design, or simply an architectural primitive such as flip-flops and LUTs. A pin is the input or output of a cell, while a port could be an input or output of a top-level module, usually a device pin. A NAT refers to an interconnect between two instances of primitive. Finally, a clock is a port, NAT, or a pin that drives sequential element in the FPGAs. Now, what happens if we apply multiple timing exceptions to the same node? To avoid conflicts in the constraints, timing analyzer has a set rules of priority that it follows as shown here. Set clock groups and set force path will have the highest priority, overriding other constraints, followed by set max delay and set min delay. Set multi-cycle path comes next. So far, we have discussed the importance of static timing analysis, but it is not without its limitation. First and foremost, STA does not check for clock domain crossing, also known as CDC paths. It is the responsibility of the logic designer to ensure that these transfers are being taken care of in order to ensure any potential method stability issue is minimized. The same applies to timing exceptions. While applying constraints like force path and multi-cycle could help resolve timing violation, it must be ensured that this circuit has been designed in such a way that these constraints could be applied. We all know digital signals have discrete time events and logic levels, which makes STA possible because it focuses on the relationship between clock edges and signal transitions. Analog signals, on the other hand, change continuously over time and can take on an infinite number of values, which means STA cannot be applied on them. Finally, STA might not be ideal for unknown values. In digital circuits, and X often represents unknown state and can complicate timing analysis because they introduce uncertainty into the signal values. When X is present, timing analysis may yield uncertain results, leading to potential false timing violation or missed critical path. Now that we have the basic knowledge of timing analysis, let's look at how we can utilize them in Lattice Radian software. We will start off with understanding the high-level design flow in Lattice Radian. On a nutshell, Radian is an intuitive tool that takes user designs from early phase of a design cycle, such as design entry, all the way to hardware implementation targeting any Lattice FPGAs. Design entry is where the design for the FPGA is being created or entered. This includes design files using hardware descriptive language, such as VHDL or Verilog. This is also where timing and physical constraints are included. Debug capability could also be added if needed. Once the design and any associated files are ready, the synthesis engine in the tool will synthesize the HDL design into a structural netlist made of Lattice user primitives. During this stage, many steps are being taken to optimize the netlist. Constraint propagation involving IPs also take place at this stage. After synthesis, the tool will map the logical primitives in the post-synthesis netlist file to physical primitives. This is also where physical constraints like pin assignment and placement constraints will be processed. Then, the tool takes the mapped physical primitives and places them at specific locations on the device before being routed using the available routing wires available in the device. In this place and route stage, a large amount of optimization will take place in order to reduce routing delay that will negatively affect the timing performance. Finally, in the export stage, bit stream could be generated and downloaded to the device using a configuration programmer. Optionally, IBIS model and gate level simulation files can also be generated here to verify the functionality of the design. Radian software supports several design constraint files depending on the synthesis tool selected and whether it is for pre-synthesis or post-synthesis consumption as shown in the table. The SDC file is recommended since it can be used on both LSE and Simplify Pro synthesis tools. Also, there are two types of constraints, the first one being timing constraints, which are timing requirements for the design, while physical constraints, which affect the physical layout of the netlist. We will talk more about the difference between pre-synthesis and post-synthesis constraints in the coming slides. Radian supports two types of timing constraints, which are pre-synthesis timing constraints and post-synthesis timing constraints. Pre-synthesis timing constraints are entered and processed before synthesis, where the target nodes are in the logical domain, which corresponds directly to the names written in the RTL files. These constraints will then be automatically propagated to the later stage of the flow. Post-synthesis timing constraints, on the other hand, refer to the constraints that will be consumed after synthesis, such as map and par. Here, optimizations happen in the physical domain. Because of that, the target nodes are specific to the device and synthesis tool used, and hence portability is somewhat limited. The timing constraint editor in Radian, also known as TCE, provides an effortless method for users to insert timing constraint intuitively without having to memorize any syntax. Once launched, users can specify the clock details such as clock name, period or frequency, and the object clock. The corresponding SDC constraints will then be reflected to the targeted .sdc or .pdc files. Users have the option to do this either in the pre-synthesis or post-synthesis timing constraint editor as shown in the snapshot here. Regardless of the type of timing constraints being used, we need to understand that Radian is timing driven, which means timing constraints are consumed throughout the flow from synthesis all the way to place and route. However, as we go further down in the design flow process, any timing violation that occur becomes harder to fix. In other words, the constraints at the earlier stage will have impact on all the subsequent stages in the design flow. As mentioned, Radian supports timing analysis at multiple implementation stages, from post-synthesis timing analysis, map timing analysis, to place and route timing analysis. These can be optionally enabled on the Radeon software task detailed view window as shown on the right. In post-synthesis timing analysis, the output file extension is .tws. And here, since it has no information of place and route, the delays are estimated and less accurate. It is typically used to identify constraint issues such as syntax error without requiring the tool to run through a full compilation. Next, map timing analysis improves the accuracy by modeling the actual netlist components and estimated routing delays, and could be used to assess timing performance or identify bottlenecks in the design, such as long logic level. The file extension here is .tw1. Path timing analysis, on the other hand, is based on actual placed and routed netlist, and hence is the most accurate. It has a file extension of .twr and must be used as final timing sign-off. Now that we have discussed on how the constraints are inserted and consumed by Lattice Radeon, let's look at the output from the tool, which is the timing reports. After compiling the design in Radeon, a timing report will be generated. The timing reports at post-synthesis, map, and place and route all have identical contents as shown here. The report has 4 sections, the first section being the timing overview, which gives an overview and summary of the timing analysis of your design. Section 2 and 3 cover the setup time analysis at high temperature and low temperature corners, respectively, while Section 4 covers hold time analysis at low temperature corner, which is typically worst. We will discuss more on each of these in the coming slides. Let's begin with timing overview. In Section 1.1, the report contains all the timing constraints that are processed by the tool, including the ignore ones. Here, users can cross-check if their constraints are taking effect as intended. Next, the constraint coverage subsection displays the percentage of timing constraints in the design. 100% coverage means all the paths in the designs are covered in timing analysis. Subsection 1.3, which is the overall summary, gives an overall roundup of all the setup and hold timing results. Timing errors indicates the number of endpoints which violate setup or hold violations. There is also a sum of the total negative slacks in terms of setup and hold. The unconstrained report shows the paths that are not constrained either at the start points or endpoints of each path. Suggested timing constraints are provided to constrain the given path, as shown in the diagrams here. The next subsection of the report is similar, but is targeted for input and output ports. Ensure that these I/O ports are constrained accordingly, for example using set input delay and set output delay. Besides I/O ports, there could also be nets in your design that do not have any clock information. In this case, check if there is any clock definition at the top level port, or a generator clock constraint is needed on this net. Now, let's move on to the main timing analysis portion of the report. The clock summary subsection is available in both the setup and hold timing corner sections. Here, all the information of each clock domain is shown, including the clock constraints, target frequency versus the actual or maximum achievable frequency. The MPW, also known as minimum pulse width frequencies, are also shown here, which are basically based on silicon limitation. The clock domain crossing section shows the slack with any other clocks that connect with the given domain. This is a data path that has different clocks for its starts and endpoints. The endpoint slacks subsection lists the endpoints, slack, and total setup number of endpoints with negative slack. In this example, the worst case setup slack is -14.18 nanosecond, and there are a total of 76 endpoints that fail to meet timing. Let's take a closer look at the detailed report subsection. Here, the worst paths for setup and hold are shown. The path begin and path end display the source and destination nodes respectively, and these can be sequential elements or I/O ports. The source clock and destination clocks are the clocks that fit these endpoints respectively and could be single clock or clock domain crossing paths. The logic levels indicate the number of combinational logic in the path, and the larger the number, the harder it is to meet setup time. The delay ratio provides a breakdown between routing versus logic delay. Clock skew indicates the delay difference between the source and destination clock, and is usually small for single clock transfer. Next, setup constraint is the timing requirement for this path, which is derived from the timing constraint. Common path skew is similar to clock skew, but now the delay in the common portion of the path is taken into consideration. A larger value typically means a smaller clock skew. Finally, path slack provides the calculated slack for that particular path. A negative number means that this path fails to meet timing. Next, in the detail report section, the path is broken into 3 parts: source clock path, data path, and destination clock path. The source clock path provides information of the clock that feeds the source node, including the clock start point. The cell name, the incremental and cumulative delays, its delay type, and also number of fanouts are displayed here. The same information is available in the data path section. We can differentiate the type of delays in the data path by looking at the names. Interconnect routing delay is represented by net delay, while the reg_delay here indicates the delay of the source register. Here, the delays for CCU2 component or carry chain unit are also shown. On the next column is the delay value of each component, and when they are added up together, this is represented by the total or cumulative delay on the right. Finally, the fanout of each of these components are shown on the far right of the report. In the destination clock path section, we have additional information. The constraint value indicates the setup requirement. Here, the value of 6.734 nanosecond, which is what user input in the SDC constraint. The general formula for setup slack calculation is required time minus arrival time. The arrival time is the sum of source clock delay and data path delay. And in this example, this is 7.543 nanosecond. Required time, on the other hand, is the addition of setup requirement with destination clock delay minus the device setup time. In this example, it is 9.689 nanosecond. The difference between the arrival and required time is therefore 2.146 nanosecond, and this means that this path meets timing. Now that we know how to constrain our designs and understand timing reports in Radeon, let's move on to the final topic, which is timing closure with Radeon. Timing closure is important because it ensures that our designs meet the required timing performance and at the same time function correctly as intended. This process has become more and more challenging as designs grow in complexity and sizes, often resulting in multiple iterations. It has become more relevant in FPGA development because when fully planned, the process will become more time and resource consuming. Hence, it is always advisable to plan ahead in the early phase of the design cycle. Some of the considerations that will affect timing performance includes device selection, extra timing margin or guard band, and the complexity of the design. Listed here on this page is the 3 golden pillars in achieving good timing performance. A good RTL coding style will go a long way, where the code should always be written with FPGAs in mind due to its inherent restrictions. Whenever possible, reducing signal fanouts and adding pipeline to critical paths will always have a positive impact to the design performance. For complex operation, consider if pre-calculation could be performed to reduce the complexity that limits the performance. For multi-bit buses that are timing critical, explore if increasing the signal width but running at half the speed could be acceptable. Next, let's look at the software tool settings. In many cases, the settings provided by the tool could be used to target performance. Play around with different settings and see which works best for your design. Take note that there is a trade-off between performance and runtime and resource usage. Users can also perform targeted overconstraint on recurring critical paths so that the tool could prioritize this path. Finally, it is highly advisable for designers to understand the hardware architecture of the targeted devices. Hard blocks such as RAMs and DSPs are dedicated resources with high efficiency, so that should be considered. The same goes to the location of peripherals and hard IPs because these have fixed locations. Therefore, it is not advisable to have critical signals having long routing delay to these blocks. Finally, consider the pros and cons of global versus local routing, as each of these will have significant impact on the routing delay. The diagram here shows how manual duplication on high fan-out signals could help in timing closure. On the left, the blue box is a source register with large number of fan-outs, and those that are placed further away would fail to meet timing. Now, by manually duplicating the registers as shown on the right diagram, the fan-outs have been reduced and the distance to the furthest destination node have also been shortened. Radeon provides multiple settings that could impact timing performance, from synthesis all the way to place and route. Shown here are the synthesis settings that will affect timing performance for Simplify Pro. The details of each setting are shown when they are enabled or disabled in the GUI. Similar settings are also available in LSE. In place and route, here are the settings that will affect timing performance. While not directly affecting timing performance, Radeon has features that can help identify bottlenecks in a design. For example, users could cross-probe from the timing report to other tools such as Netlist Analyzer and Physical Designer to better visualize the contributing factors of timing failure, such as long logic level and far logic placement, which will be shown in the subsequent slides. In the top diagram, the Netlist Analyzer view shows the selected path, and from here, we can see that the number of logic levels between the source and destination nodes. That, combined with the Physical Designer view at the bottom, shows the actual placement of this logic on the device. In this example shown here, it is obvious that the source and destination nodes are placed rather far apart. We can also use floor planning in Radeon to group logical components together in any desired locations using bounding boxes or B-box. This can be done easily in Physical Designer GUI. In this example, the B-box is highlighted in black, and the tool will place the constraint registers inside. This is helpful for paths that fail to meet timing due to far placement. Finally, understanding the architecture and making full use of it can lead to significant performance improvement. Shown here is C2 out delay of the RAM block in Lattice R1 devices. Pay attention to the size of the RAM and also the usage of internal registers. From the table, it is obvious when the output of the RAM blocks are enabled, the C2 out delay is much lower and hence will significantly help timing performance. The same applies to DSP blocks, where in this case, the usage of the output register and the size of the DSP bits will also greatly influence the final performance. In summary, timing closure should begin early in the design cycle, as it gets more challenging to make changes or optimization later in the design flow. Since Radeon is fully timing driven, the design should be correctly constrained, including achieving high coverage, and timing exceptions should be included if applicable. Always review the reports to see if any constraints are dropped or ignored. It is also good to understand the targeted device architecture, including the hard block resources and IPs being used. When there are timing violations, analyze the timing report carefully, find out why it fails timing, and optimize the path accordingly. This can be done through RTL optimization or using other software settings. Radeon provides a handful of built-in tools to assist users in the process of timing closure. Now that we are done with the presentation, let's look into some of the frequently asked questions. The first question that we often got asked is, are input and output constraints really necessary in FPGAs? The answer is yes. They are needed to ensure that data that is coming into and going out from the FPGAs are being captured correctly. However, if the signals are truly asynchronous or non-timing critical, this path can be set to false path. Next, how does process variation affect static timing analysis? Well, process variation in silicon devices is due to fluctuations in the manufacturing conditions. This causes differences in timing delay characteristics, but the timing model in a tool would have already catered for the worst case scenario. The third question, how do we handle clock domain crossing or CDC signal path? If they are asynchronous, this path can be set to false path. Else, they should be handled carefully to ensure functionality is guaranteed, such as using FIFOs or synchronizer. Next, do I need to create timing constraints for PLL in lattice radiant software? Well, users would only need to constrain the input to the PLL. The PLL generated from the IP catalog will be automatically constrained based on the parameter set. Another commonly asked question is, what is the difference between distributed ramps and block ramps found in an FPGA? Well, distributed ramps are implemented using FPGA's core logic, such as lookup tables, and are generally smaller in capacity, while block ramps, on the other hand, are dedicated memory resources at specific locations designed for larger memory storage.